Good afternoon, everyone. So thank you for to the organizers for such a fantastic conference so far. Hopefully my talk doesn't change that. And thank you for accepting, I guess, my invitation to myself for coming. So you've all been a very polite audience so far. Feel free to interrupt me at any time with questions. There's not really much point in me being the only person that follows this talk because I already know all the stuff already. So yeah, if we don't cover everything, that's completely fine. Yeah, so I'm going to talk about existentially closed groups and why computability theory has something to say about them. I don't expect that many of you will be familiar with existentially closed groups or even some of the finer parts of computability theory. So I'll try to introduce that. And hopefully this will be somewhat understandable. So the outline will sort of be, I'll give the definition and motivation. Then I'll talk about some of the structure of existentially closed groups. And then hopefully if I have time, I'll talk a little bit about the structure of the class of existentially closed groups. So existentially closed groups are sort of essentially groups where I can solve any existential or which have a solution to any existential which is consistent with the theory of the group. So formally, M is an existentially closed group, which I'll write as EC group, if M is a group and for any quantifier-free formula in the language of group theory. So I can think of this as sort of a collection of equations and inequations. Group theory, E of X, M. So these are just elements of the group. So I'm allowed to have coefficients, which is consistent with M in the sense that there is some group containing M which solves it and solves Phi, then M also solves Phi. So any first order quantifier free property, which is consistent with the theory of M, is solved in M. So just to get some intuition, the existentially closed groups are very large, very rich. EC groups are not finitely generated. However, they're determined up to isomorphism by their finitely generated subgroups. Not by are determined to iso by finitely generated subgroups. So somehow, if you can understand the finitely generated subgroups, you can understand at least the algebraic structure of the whole group. There might be other facts that I want to say. Oh, so there are lots of so every group embeds into an existentially closed group of the same cardinality plus Aleph naught. The existentially So since we're doing computability theory, I'll be focusing on countable existentially closed groups, but you can consider them in more generality. And so as a consequence of this, because any countable existentially closed group can only contain countably many finitely generated subgroups, but there are uncountably many finitely generated groups. So there are continuum many countable existentially closed groups. Okay. So they're sort of large in some sense. They're kind of sort of universal. That they contain, the class of them contains every group, and there are lots of them. And they're related to computability theory. So one of the early results on existentially closed groups is due to, in part, to Neumann, who's a group theorist, and McIntyre, who's a model theorist, and they showed that for a finitely generated group, G, there was an order I want to put these in. Okay. G has solvable word problem. G, or I'll say this in a in a way that is sort of more natural from a computable structure theory perspective. So group theorists would say G has solvable word problem. I'll say G is computable. So its multiplication table is computable. If and only if G embeds in every EC group. So somehow the entire class of countable existentially closed groups know what computable means. So I'll draw a picture just to kind of keep track of what's going on. Let's draw this picture here. So if I look at here's all the collection of groups with solvable word problem. If I look at all of the existentially closed groups, their intersection is exactly this class. Okay, and as computability theorists, it's sort of natural to ask, well, does this relativize? So what I mean by that is G being computable sort of means that with a Turing machine with an empty oracle can write down the multiplication table of G. And so if I take a group which is built by a Turing machine with something on its oracle tape, then can existentially closed groups kind of classify that relation? So I'm going to write down something vague enough to be sort of true, but false if you interpret it in the way that it sort of looks like it should be interpreted, but then I'll make it true. So don't quote me on this yet. I won't write theorem yet. So for a finitely generated group, for finitely generated groups, G and H, following are equivalent. So G is computable from H. And G embeds in every EC group that H does. So this would sort of be a relativization of this theorem to H, or to G, I guess. To H, I guess, yes. So with information about H, I can compute G is the same as G embedding in every existentially closed group that H does. So this is false for Turing reducibility, but it turns out that or what Siegler showed, so this is the theorem due to Martin Siegler, is that if I take sort of a finer notion of reducibility, then this is true. So there is some sort of computational way to characterize embeddability in existentially closed groups. So I don't want to say what this Siegler reducibility is, because even if I tell computability theorists about it, I've gotten a response like, what the fuck? A little bit complicated. It's not particularly natural, but what this theorem is saying is that somehow it captures the proof of this theorem shows is that it sort of captures like the kind of syntactic notion of provability in groups. And so how does it behave? Well, it's defined purely computability theoretically. So I've given you an if and only if, and I haven't told you what one of the things means, so maybe it could be sort of trivial, but it's defined purely in terms of computability theoretic ideas, sort of the minimal class in the degree structure that this gives us. So much like we can go from Turing reducibility to Turing degrees, we can go from Siegler reducibility to Siegler degrees, and there's a minimal class given by the empty set, and it's exactly the same as the minimal class for Turing degrees. So the computable sets are exactly the things which are minimal in Siegler reducibility. Computable sets, which is essentially the content of this theorem. And oh yes, and it's finer than Turing reducibility. So a Siegler reducible to B implies A is Turing reducible to B, but not vice versa. Okay, so this was sort of the background on existentially closed groups. And we see that if we want to understand existentially closed groups, they're these big complicated groups, but maybe if we get a hand on their finally generated subgroups, which are sort of maybe easier to understand, at least classically in group theory, then we could understand the existentially closed groups. And if we want to understand the class of finally generated subgroups, we kind of can't help but be doing computability theory, at least somewhere in the background. So what I did in my thesis was essentially ask the question, well, like, okay, let's just study existentially closed groups as computability theorists. And if you're a computability theorist and you have some structure, the first question is like, how complicated is it to build an example of this structure? So question, how complicated is it to build an existentially closed group? And I'll answer this question. I'll kind of write a collection of theorems sort of as a picture. Okay, I'll try to make it clear what part of this picture is mine. Okay, so if we're looking at the Turing degree, so let's go back into the Turing degree world. Where there's a minimal class, the computable sets. As Noam said yesterday, there's this class of sets which are equivalent to the halting problem, which we call 0 prime. And then you can kind of iterate this, you get 0 double prime, so on. All the Turing degrees, here's all the things which are below 0 prime. And the answer to the first question is that it turns out that the existence of an existentially closed group is exactly at the level of the halting problem. Okay, so this is kind of two theorems wrapped up into one. So on the one hand, we have to show that using an oracle for the halting problem, that we can build an existentially closed group. And what this essentially comes down to is that you're kind of building your group dynamically. And I want to at some point ask the question, I want to decide whether a given equation should be in my set or not in my set. And the question I want to ask the halting problem is this consistent with what I've built so far in the axioms of group theory? And so with an answer to that question, I can build an existentially closed group. And then on the other hand, you have to show that, so there's no way to build an existentially closed group without asking a question of that form. And so what this result is really showing is that in some sense, to build an existentially closed group, I'm required to be able to answer questions in general about the consistency of a finite collection of sentences in group theory. However, if you look at the proof of this, as you're building your existentially closed group, you kind of get a kind of larger and larger finitely generated groups containing the information that you've built so far. In order to build the halting problem into your construction, you have to walk all the way to infinity to get 0 prime. There's at no point in this construction are you guaranteed to have some finitely generated group which computes the halting problem. On the other hand, we know that existentially closed groups are determined up to isomorphism by their finitely generated subgroups. So somehow the finitely generated subgroups, the class of finitely generated subgroups knows the entire existentially closed group. But this theorem doesn't tell me that they know the complexity of the finitely generated group, of the existentially closed group. So I'll write down the next theorem, and maybe this will make it slightly more clear what I'm getting at here. That I showed. Yeah. Okay, this is not a very accurate picture here. Right, so essentially, in order to, let's see, you compute all the subgroups of an existentially closed group, all the finitely generated subgroups. Requires a PA degree. Okay. So what's going on here? This is saying that, so existentially closed groups are built up from their finitely generated subgroups. The entire existentially closed group has to compute 0 prime. But it's possible to find some big complicated existentially closed group, all of whose finitely generated subgroups are sort of quantifiably below 0 prime. So it's possible to find existentially closed groups which are somehow big complicated objects which are built up from much, much smaller objects, kind of necessarily arranged in a somewhat haphazard way, so that in the end you get the halting problem, but sort of at every finite stage you have something which is far below the halting problem. Okay, so PA is short for piano arithmetic, and the idea of a PA degree is that you're computing a complete extension of piano arithmetic, but really what a PA degree means combinatorially is that a PA degree allows you to find a path in a computable binary tree. So what this result is kind of telling you combinatorially is that if you want to sort of build a collection of finitely generated groups, which you can put together to get an existentially closed group, you're going to have to at some point do something where you kind of are either maybe completing a theory or you're building some binary tree and looking at sort of paths in the binary tree to get your finitely generated subgroups. So sort of by, I guess I should say that the other half of this result is known. It was known to McIntyre and Siegler. They showed that any existentially closed group contains a finitely generated subgroup with unsolvable word problem. In modern terminology, they showed that it contains a finitely generated subgroup of PA degree. So going back to this picture, all of these, there's no existentially closed group, which is just these purple guys. Every existentially closed group contains something with unsolvable word problem.
Well, the PA degrees can be low, right?
Yes, that's what I mean by quantifiably.
Okay.
Yeah, so what Andre is saying is that the PA degrees, right, the combinatorial information is that they're computing paths in binary trees, but kind of the structural information is that it's possible to find a PA degree such that its jump, so this jump operator that no one was talking about yesterday, is only at 0 prime. So somehow, okay, this degree is not computable, but like it's sort of in some sense like very, very close to being computable. If I want to understand getting information about whether or not a program halts relative to this degree is no more complicated than getting information about whether a program halts relative to just normal computing. So How much longer do I have?
Let me just double check that. So I have lost track, but I think that if you go until 3, that should be fine.
Okay, great. I'll,
Be like 15 minutes.
okay, then I have a little bit of time to talk about, the Ziegler degrees. So, right, so what we've seen so far is that using computability theory, we understand sort of better the structure of a given existentially closed group. What Ziegler reducibility allows us to do is to sort of understand the structure of existentially closed groups as a class and how they sort of relate to the kind of, like, each existentially closed group picks out some collection of finitely generated subgroups. And by understanding Ziegler reducibility from a computability theoretic standpoint, we can get structural information about the class of existentially closed groups. I think I've lost count, but I think I'm at 2 now. So, okay, so this will be slightly technical, but I'll try to interpret what it means if I've written it down. So this is a JK. So this is a joint work with Josiah, Jacobson, Grocott. So that's a hyphen. Stefan Lemp. So we showed that every finite distributive lattice embeds as an initial segment of the Ziegler degrees. Okay, so one particular case of this is this lattice. So embedding this as an initial segment of the Ziegler degrees says that there's, okay, here's the minimal Ziegler degree, which is just the computable sets. There is a Ziegler degree such that there is nothing below that degree other than the computable. It's not computable itself. So running this through Ziegler's theorem, there are groups such that if you know that they embed into your existentially closed group, okay, you have that every computable group embeds into every existentially closed group. So you know that the computable groups embed, but the only extra information that you get from knowing that this group embeds is the groups which are star equivalent to it. So it's kind of as little non-computable information as you can possibly get. And as a consequence, via work of Andre Nice, this implies that the 3 quantifier theory of the Ziegler degrees as a partial order is undecidable. So if I want to ask questions about sort of what kinds of configurations of kind of relative embeddability of finitely generated groups into existentially closed groups, once I get to 3 quantifiers, there's no way I can answer those questions computably. Right? So proving purely computability theoretic results, we get sort of purely algebraic theorems out of them. And it's been a lot of fun to work with. So thank you, and happy Thanksgiving, everyone.
So much, Isabella. We just stop the recording.